It's my honor to be here to talk about my research named Graph Neural Network for Robust Public Transit Demand Prediction. Travel demand and mobility patterns vary from time to time and exhibit a strong level of uncertainty. Forecasting the demand and the demand uncertainty is important and necessary to optimally determine bus fleet size, vehicle size, bus transit lines and networks, and scheduling. Although there have been fruitful studies on predicting passenger demand for public transport, existing studies often focused on deterministic demand forecasting or mobility analytics. The confidence interval or precision level of the estimates has received much fewer attention. Thus, this work aims to explicitly consider the confidence interval for demand prediction. Alternatively speaking, we will quantify the precision level of the demand prediction. The proposed confidence interval is an estimated interval for the demand. It's associated with a target confidence level and computed based on the observed data. It can be helpful in future service planning and operation optimization problem, since it provides a more reliable representation of demand. It directly relates to the effects and robustness of the planning and operation decisions. Then let's move to the problem formulation. Many existing studies on demand forecasting divided the whole city or area in concern into multiple squares, triangles, or hexagon grids. This can be readily done with the model proposed in this study. However, differently in the experiments in this study, we consider the administrative areas for demand prediction based on the postcodes. Smaller region sizes or types can also be considered. In practice, many relevant planning and management activities are indeed administrative region-based. Estimating the demand at the administrative region level can be useful in many occasions and can provide evidence for policymaking at the region level. It's also noteworthy that administrative regions often have unique features or functionalities, such as land use and demographic attributes. In practice, urban features partially govern traffic patterns and thus further governs origin destination demand patterns. Thus, in this study, we participate the city into the regions based on the postcode tabular. Then we formulate the routes between the origins and the destination. In these slides, there are the settings for the demand sequence, and prediction function. We use the most recent time steps historical OD demand to predict the demand in the next time step. As I just talked just now, the predicted demand interval with a target level of confidence provides a more robust way to represent the demand and better captures demand variability and uncertainty. However, the true demand confidence interval may never be obtained. Thus, we approximate the true interval with the alpha level prediction interval based on the normal distribution. Specifically, the interval can be formulated as this equation shows, and mu and epsilon are the mean and standard deviation of the estimated demand, and z times half alpha is the coefficient for the standard deviation. These values can be obtained based on quantifying the graph-based model uncertainty through Monte Carlo dropout training, which will be discussed in the following slide. Then let's move to the overall framework of this model. As shown in this figure, the overall framework consists of two components. One component is a series of gated graph convolution layers, which are applied to capture the spatial and temporal correlations in the demand profile simultaneously. Another component is a Bayesian-based module to quantify the uncertainty associated with the proposed graph-based model. The details will be introduced in the following slides. First of all, let me introduce the graph convolution network. Previous studies hold that spatially adjacent areas may have similar OD demand. However, OD demand is not only related to spatial location, but also relies on demographic attributes and land use. Graph-based deep models are able to process the data with non-Euclidean structure and extract the features from OD demand data. Therefore, we define an undirected graph G which consists of node H and matrix. In detail, an OD pair is represented by a node in the graph constructed. This node in the graph defined is different from the node usually defined in the physical transport network. An edge between two nodes in the graph is used to indicate the correlation or similarity between the demand patterns of two OD pairs. If the demand patterns of two OD pairs are correlated to or above a certain extent, we add an edge between the two nodes in concern and set the corresponding value in the adjacency matrix as 1. Otherwise, the value is 0. The adjacency matrix is determined by the demand similarity between two OD pairs, and the Pearson correlation coefficient is utilized to quantify the similarity. Based on the constructed graph, following the definition of graph convolution layer, the result of the graph convolution layer can be calculated as this equation shows. Then, gating mechanisms is adopted in the layer to form the gated graph convolution layer and capture the nonlinearity and decide which parts of the linear transformation can be passed through the gate and thus contribute to the final prediction. Then let me introduce the mechanism of the set of the gated graph convolution layers. One gated graph convolution layer has limited capability to capture long-term temporal relations in the total number of I-time steps. Thus, we define another number m that is smaller than I, the total number of time steps. Based on the input OD demand data x, we then can define I minus m plus 1 different x new, and x new involves less time steps than x. The matrix in the lower left corner in this figure provides an example of x new for illustration. Such an operation means that one gated graph convolution layer acts on m time steps of the demand data. It could extract the spatial correlation among all regions within m time step. Therefore, only I-1 divided by m-1 gated graph convolution layers are needed to capture the temporal dependencies in I-time steps. It could decrease the number of iterations and improve the accuracy when compared with recurrent neural network-based models. The proposed model is able to capture the spatial and temporal features by the several gated graph convolution layers before the last output layer. Thus, it's not necessary to also use the gated graph convolution layer as a final prediction layer. And due to the weight sharing mechanism of convolution neural network, it needs fewer parameters than the fully connected layer. Thus, at last, we choose convolution neural network as the output layer in our model to extract the dependencies for prediction. Then we adopted the Bayesian inference to model the uncertainty of the demand. Bayesian deep learning based on Monte Carlo dropout assumes that each weight and bias should obey a certain distribution instead of a certain value, which leads to an interval of the demand with a certain level of confidence. And the construction of the network with dropout is not changed, so the prediction results are still reliable. The first step of the Bayesian inference is to randomly drop out some neural units with probability before each layer, and then do the forward passes through the network. We could get the prediction demand. Then repeat the aforementioned steps for several times and could get a set of predicted results. At last, calculate the average value and standard error to measure the prediction uncertainty. Now let me introduce the dataset used in the experiments. It's collected from Sydney, covering main public transportation surveys from April 1st, 2017 to June 13, 2017. It covers about 6.3 million users. And in this study, we focus on forecasting the demand of buses. And the different regions have different sizes, and in this figure, we show the partition of Sydney based on the post code, and the areas shaded in purple are the study units. Different regions have different sizes, and the average value is about 7.8. In order to protect the privacy of users, the data doesn't involve personal information, which can be used to identify the individuals. In the experiment, we choose all bus lines information, including tap-on and tap-off location, time, corresponding administrative area, and the number of passengers getting on and getting off. We divide the whole dataset into 3 mutually exclusive subsets. The first 17 days data are used for training, the last 10 days data are used for testing, and the rest for validation. And the demand data is normalized by min-max normalization for training and rescaled for evaluating the prediction accuracy. And in the experiment, we have tested 3 different lengths of time steps for demand prediction, including 1 hour, 30 minutes, and 15 minutes. Then let me talk about the experiment results of this method. This table summarizes the results regarding prediction accuracy for the proposed method and the listed tools in the literature under different time resolution for demand forecasting. Several observations are made based on the results. First, the 3 traditional machine learning methods, the ARMA, LR, and HA, have relatively larger RMSE, MAE, and MAPE. This is partially due to their inability to capture nonlinear relations among spatial and temporal information for the forecasting. These results imply that there exist nonlinear spatial temporal relationships in the demand data set that non-deep learning models cannot capture well. Second, ARIMA yield relatively poor in performance. A possible explanation is that it involves several parameters such as the order of the autoregressive model, the degree of differency, and the order of the moving average model. It's not straightforward to obtain the optimal setting of these parameters. These indeed have been reported in some previous works. Thus, the ARMA may yield relatively poor performance. Third, the listed remaining neural network-based strategies, including GRU, GCRN, LSTNet, and SDGCN, are able to predict the OD demand more precisely, since they are able to capture the nonlinear relations. And the good performance of the LSTNet is partially due to the skip connection. This operation of the skip connection can also be adopted in other models to enhance the forecasting performance. However, GRU and STNet are less interpretable. For instance, in terms of the correlations among the OD pairs, since they didn't explicitly analyze the spatial correlations. Compared to them, our model based on the graph convolution network is more interoperable, where the correlation among the OD pairs based on the adjacency matrix are identified and more intuitive. In general, the results indicate that our model can capture spatial temporal correlations more accurately than others when predicting OD demand. And this table compares the results of the proposed model and for deep learning based strategies, which would combine with Bayesian approximation. In experiments, the level of confidence value alpha changes from 94% to 98%. The results show that over 3 time periods and 5 confidence levels, our model achieves a higher coverage proportion within a shorter prediction interval. And this means that the proposed model can give more accurate prediction in a smaller range. In conclusion, this study makes the first attempt to combine the Bayesian neural network with OD demand forecasting for predicting demand confidence interval. It provides a reliable way to represent the demand and measure the uncertainty of demand. The output can be used for public transit planning and operation optimization problem. The developed techniques may also be applied to other domains, such as human mobility uncertainty analysis and traffic flow variability. In the future, this study can be further extended in many ways. Firstly, the current work can be extended by adding more information into the neural network, such as the demographic attributes and the point of interest of the areas. This may further improve the prediction accuracy. Secondly, further study may also explore the time series mutation problems based on the demand forecasting. And moreover, we may utilize the graph network in alternative manners in order to predict the demand. For instance, we may consider nodes in the graph as zones in the real world and the edges in the graph as a demand between the origin and the destination, and develop further related techniques. That's all for my presentation today. Thank you.
Thank you, Kan. Do we have any question from the audience about the presentation? Anyone wanted to ask a question? Please feel free to unmute your mic.
I have a question. So well done, Kan. I missed the first few slides. Maybe you mentioned. So in this work, what you have done so far is you create a undirected, unweighted graph between different zones, right? So you don't look at the individual stops, right?
The undirected graph is between different OD pairs, not the zones.
So what are the origin and destinations? Are they zones or are they bus stops?
Origin and destination are the zones.
Okay, so and why undirected? Why? Because usually and unweighted as well, right? So you just have the adjacency matrix, not a weight matrix.
Yeah, since the OD pair is such like for instance, if we have two zones A and B, thus the OD pair is AB and BA. Thus we defined the node as AB and BA.
Yes.
They are undirected.
So do you predict the demand from A and B to A separately, or no? You only have one demand on the link between A and B?
Just to predict the demand from A to B and B to A.
Okay, so you're not okay, so you actually have a directed network.
Yeah.
Okay. And you also so the OD matrix is actually a weighted directed network, right?
Wait,
Weighted, the weight on the links is the number of trips going between A to B.
yeah,
You predict the number of trips, or you just say whether there is a trip between A to B?
the number of the passengers
between A to B
yeah,
and B to A.
yeah,
And you only use, for example, historical data to predict future.
yes.
Did you exclude like weekends, or how did you deal with different time of the day and different times of the week?
No, we haven't do the experiments like that.
So what days and what times of the day you worked with the data?
I used the data from April 1st, 2017 to June 30, 2017, and include 24 hours in one day.
So did you exclude Saturday and Sundays, or no?
No, we didn't.
Okay, so of course, I think obviously that's one thing you can think about, because Saturday and Sunday have totally different demand patterns, and it may improve your model if you exclude them. And you also predict, okay, so you predict hourly demand between all these. Why didn't you do from every bus stop to another bus stop? Why did you have to do zoning?
We have did some experiment about this bus stop to that bus stop, but we haven't put the results on this presentation due to the time limited.
Good. Well done. Good job.
Thank you. Thank you for the question.
Yeah.
Thank you, Miad. Anyone else?
I actually have another one if nobody has one.
You go.
Because I've done some similar work. We're doing some similar work, and we have a paper in Part C under review on not on demand estimation, but mainly on how to, we don't call it demand estimation, we call it building the, creating the demand network from smart card data. So there are a lot of challenges, including many people tap on and don't tap off. There are transfers. So how do you deal with those? Because somebody may get off a bus stop, but the final destination may not be at that zone. They may get in another bus, or they may get on a train or something like that. So there are some big issues like transfer, missing tap on, tap offs. Are you going to deal with those, or no? You make assumptions and then you focus on other parts.
Yes, maybe this way in this work we just exclude the reports. Maybe they just have tap on, but they don't have tap off. We just exclude this information and do the prediction. But we think in our study we predict the prediction interval. In that way, I think maybe it can partially present the information that maybe we exclude. So we think it's robust, but maybe in the future we can consider about the abnormal records.
And what percentage of the data you exclude that doesn't have tap off or tap on? Do you know?
We didn't put that in this presentation, but I forget the details.
That's okay. Because if it's large, if it's relatively large, that really affects the demand. Yes, you're doing a demand estimation, but that wouldn't be the real demand. So it would be a misleading.
I remember it's a relatively small range.
Okay. And also knowing the number of transfers is important, especially if you do only, but anyways, not transfers, missing trips. Working with the smart card data, there are a lot of challenges. So you may want to think about some of those in your future work.
Okay, thank you.
Good job, well done. I really like this topic.
Thank you.
So there is a question before Miad asks another one from the chat. So Baman is asking, actually on the slides you are showing now, why are some zones excluded in your analysis? For instance, the white zones in the map. Can you comment on this, Can, please?
Since there only exists a very small number of records in the, maybe in one day, it only has less than 10 or less than 20 records. Thus, we think it's unnecessary to predict the demand of these regions.
Okay, so it's because those suburbs in white, they're too low demand, so you excluded them to avoid any. Okay, thank you. I had a quick question myself, if I may. You mentioned you split your data into training, testing, validating. Can I ask what percentage of data is
sorry?
used? What percentage of data is training? What percentage is testing, and one is validating?
We use 70 days for training and 10 days for testing and 10 days for validation.
Okay, all right. Yeah, that sounds about right. Okay. Okay, the presentation was great. Any other question? We have 3 minutes left. If anyone has another question for Can.
I have another one. Sorry.
You go.
And when you do you have 3 different lengths of time steps, 1 hour, 30 minutes, and 15 minutes. So do you have, I assume you also consider what's the right terminology to use? Like the lagged variables, where, for example, the number of trips between each OD pair in the previous time interval in T-1, T-2, T-3 will affect the number of the demand at time interval T. Is that right?
Yeah.
Is that taken into account?
Yes, we just formulates the demand as this slide shows.
Okay. So you have all of those. Got it. Cool. Yeah. Excellent.
Thank you.
So there is another question on the chat from How are the training, but that's the question I just, okay, no. So the first question is, how are the training testing data divided? And for example, is it possible to have a trip AB in testing and a trip BA in training data? So essentially, if you have an ODAB, is it possible that when you split the data across training and testing, A to B is in testing and B to A is in training?
I think this have no relation to our work, since we just divide the data sets using the time, but not the origin and the destination.
So you have all zones in all set of data, but you different time periods.
Yeah, but not destination.
Okay, thank you. Okay.
Can I ask a quick question, David?
Yeah, sure.
Ken, thanks for the presentation. I was wondering, till now, from your analysis, have you seen any trend, or do you have any suggestion on the performance of any of the public transport modes? Like, where are they? Which zones do not have enough of public transit routes or something like that? Do you have any suggestions from your analysis?
You mean other kinds of modes of the public transport, such as the ferry or light rail?
Yeah, just the public transport. Are there any zones which are which do not have enough public transport routes? Maybe can they improve on that somehow? Do you have any suggestions?
Thank you for your question. Due to some zones that have maybe the light rail or such like that. Thus, in this study, we haven't considered that, but we have another work about the 4 different modes in Sydney, including the bus, train, light rail, and ferry. And we model another framework to predict the demand of these 4 modes.
Oh, okay. Yeah, thanks.
Thank you.
Okay. So I think we're about done with the time here. So I would like to thank you, Ken, again for your presentation. And we'll have, I think, another seminar next week, perhaps another 2 to go this year. And then, of course, we'll resume the series next year. So thank you, Ken, for being there today.
Thank you.
See you all next week.
You.